Hi, welcome to the explanation video of the second round. This is a PowerPoint presentation where I will walk you through the every question along with their answers. At the same time, I have submitted the a documentation which actually clearly explains every steps in details. So without any further ado, let's dive into the explanation video. So here, if you can look into the first problem, actually, is on my screen. Which is the following: given an AVL tree storing numerical values, design an algorithm to efficiently return the sum of all values within a given range, which is L and R. So basically, we'll be provided a range L and R, and we have to find out the summation, of these values. So before diving into the solution, we have to understand first what is binary tree, and later on we'll be talking about binary search tree because in this problem we'll be using that. So binary tree basically a tree which has like two childrens, right? So this is the concept of binary tree, but it doesn't really follow any specific order or any types. It just insert values, and it grows. But the problem with that thing is we cannot efficiently search from that thing. So that's why we have binary search tree. So let's talk about binary search tree. So to understand this, you can look at this picture here. So you can, if you look at that, so let's see, without using any terminology, I'm going to explain binary search tree to you. If compare these two nodes, so you'll actually notice that this node is much larger than this one. And if you notice this node and this node, you'll see this node is actually much smaller than this one, right? So yeah, this is actually the requirement to create a binary search tree. So the left side of the node contains value less than the node's value, and the right side, which is this side, it contains the greater, values. For example, this actually opens up all sorts of opportunity for us. For example, if you think about searching 10, let's say you want to search 10 from this tree. So you can easily know, like, okay, I want to go to this part of the tree, right? This part of the tree, then you can easily get rid of this part of the tree. So which really saves time, right? Um, so this is the benefit of using binary search tree. This is what we have, or I haven't really explained here. Let's go to more in detail explanation of that. So this is actually a tree. We'll be using that tree in our code explanation as well. So here you can see we have some values, and maybe we'll do some operation based on the question we have, been asked. So and the one thing that is noticeable about the binary search tree actually is, it keeps the height difference between left and right subtree very small, So it could be -1, it can be 0, and it could be plus 1, right? So that is one thing about binary search tree. I think now it's time to go to the code explanation. So for that, I have to go to VS Code. And here I have written down, the code. So basically I have used in order traversal here. Definitely just need recursion to, implement that. I'm not gonna explain that right now because I have explained that in the documentation that I've provided. So here I'm gonna input the tree. I'm gonna insert these values, and then this is the range actually 5 to 15, and the result is 49 actually. So let's see if that is correct or not. Let's go to the PowerPoint. So if you go to this tree, let's say this is the range 5 to 15, right? Let's look at this tree. We have 5, and then do we have 6? We don't have 6. We definitely have 7. Do you have 8, 9? No, we don't actually have 8, 9, but we have 10. And then after that, we have 12 and 15. If you sum all that up, you get 49. So this is the result we got. Uh, so this is all about the you know binary search tree and AVL basically. Uh, Now let's talk about the follow-up question. So to understand that, I guess you have to know about scaling system. For example, we had uh, like this kind of tree, right? So, and we have hard coded everything. But the problem is when maybe there's millions of user and we're storing their information, in that node, it is very difficult to scale things up. So if you use that, raw code, that raw structure that I've just showed you. So in that scenario, so we can use some parallel processing and also like batching or caching. So these are the concept that can really help us to scale things up. Basically what it says, when the user grows, that time you find it very difficult to maintain the user base. Also, this is a concept of MLOps. So let's go to the second question, which is really interesting. So this is, it reads the following. Suppose you must store and retrieve large model weight files distributed across a database. Explain how B-tree supports fast search and insert operation at scale. And there's a follow-up question. How does this apply to vector lookups in recommended system? So we'll answer the follow-up question later, but the thing is, first we have to know what is B-tree, right? To understand this problem. Hopefully, I have a slide here. So, I guess you already know about the binary search tree, but B-tree is a little bit different, right? So if you, okay, without going to the definition, let's look at this tree. So the same concept. So these are the nodes actually, and we call them keys. So these are the keys of this, B tree. Now, if you look at this part of the tree, so we have seven. Sorry for that. We have seven and we have 16, right? So if you look this part of the tree, then the right side, you can see these values, you know, greater than 16, right? And if you look at this part of the tree, this value is much smaller than 7, right? But there's one thing that is new here, which is 9, 12, and this part, this node actually. So it is not very difficult to, understand, because if you look at this range, 7 to 16, so 9, 12 is in between that range. So this is how the B tree works. It helps us to find, our data efficiently, right? So this is the concept that being used in databases. So also we can use it in disk storage and large databases as well, which I have mentioned here. So basically that's the concept of B tree. Let's go to the second slide. So searching from B tree is much easier, unlike binary tree. Right, we have already understand the binary search tree, which is much more efficient than binary tree. So if you talk about binary search tree, then it's just the same, right? Because we have extra node here, but pretty much the same. We'll just have some logic to find out, where our value can be. So let's talk about 21. So let's this is a balance tree, right? So that's the thing. And if you talk about the time complexity, is order of log n. Now let's go to an analogy, because I think if you just talk about the B tree, it might be very hard to understand, what's actually going on. So if you talk about this logic, so this is a library, right? I have generated this image using Nano Banana. So this is a library. So suppose right, from that logic, the same logic. You know which section you need to go to find the book that you exactly need, right? That saves your time. So basically, that's what we've been talking about, that we need to save our time, and complexities as well. So let's go to um, the second uh, part of this slide. So I think to answer the follow-up question, we have to understand the feature vector. So if you look at that image, there's a famous data set actually. It has sepal length, sepal width, petal length, petal width at the same time. So we have a numerical value for feature, right? So if you want to hold that numerical value for the features that you have, we call that feature vector. Right. So, and also if you want to hold the item itself, we call it item vector, which will be in the next slide, zoom. So, so the feature vector basically we can call it a numerical fingerprint, right, for that specific data set that we have. So from that ML point of view, so feature vector is really handy. It can come handy because I think you have already heard about the concept, actually, like the embedding concept. So where king and queen can sit in one place, and it is very easier to find out, based on the intent, based on their similarities, we can easily find out the specific word that are looking for, specific stuff that are looking for. Feature vector can actually help us with that. So I think I have already described the item vector. Now, it is very easy to understand the follow-up question now. How does this apply to feature vector lookup in recommender system? So we have talked about B-tree. So if you talk about from that point of view, I mean, you can see the pattern actually. So when an user interact with the system look up that user's feature vector and compares it to item vectors. That's the thing. So this is how the lookup operation works. So in that from that ML context, if you're using large data sets, so you can actually do that, like this embedding, and finally find out what actually you're looking for. So also RAG-based system can actually, we can implement that in RAG-based system as well. This is something we can talk about, we can do, by the way. Now let's understand the question 3 first, then we'll jump right into the solution. So it is outline an algorithm for finding a minimum spanning tree in a distributed system. And the follow-up question is actually related to ML scenario, which is, would you use MST in that? Like maybe there's example sensor network feature selection type of problem. Before answering that, I think we just have to know what is MST. So it is also one of the core concepts of computer science. So minimum spanning tree is actually a subgraph. If you talk about, every tree is a graph. So it's a subgraph, and it helps us to understand a lot of things. For example, it has no cycle, that is one part of it. So, and if you talk about a weighted graph, there are kind of different kind of graphs, like weighted graph, unweighted graph, and basically just have to create a subgraph which doesn't have any cycle, and that's is what we called minimum spanning tree. So to find out minimum spanning tree, we have greedy methods, for example, Kruskals or prims. So these are greedy methods actually. These have, the approach is a little bit different. The premise, the main idea is the same. So let's talk about Kruskal algorithm. It helps us to find minimum spanning tree, by the way. So if I explain this from this graph, so you can see this is a graph definitely, and it's a weighted graph, and it doesn't have any directions. It's an undirected graph. So how we can create a minimum spanning tree from the given graph? That's basically very simple with the Kruskal algorithm, which is a greedy approach because it tries all possible outcomes. This is why we call it greedy approach. So to start with the Kruskal method, we have to find out the very, very lowest weight, which is this one, right? So now, yeah, let's find out that. So we have done that. So we have connection G to H. So this is the connection, right? After that, what is the most lowest, weight from here? So you can see this is 2 can be a most lowest weight, and this 2 can be most lowest weight as well. So we'll go with 2, right? Yeah, this 2. After that, we have 3, So the thing is, 3 isn't the lowest weight, right? So you can go here. But the thing is, the basic idea that I want to give you is if you add 3 here, there will be cycle, right? We don't want to do that. So that's why we can be here. After that, you have to go to 3. So that way it'll there will be cycle, right? So you don't have to go to do that. So if you do this approach, and when there will be a cycle, you just have to stop, right? So this is the basically the Kruskal approach, and it will help you finally find out a minimum spanning tree, right? Now let's go to the to get the basic idea of distributed system. So basically, as the name suggests, that the system is like there are many computers connected, with each other. Each computer has definitely their computers. They have their own processing unit and stuff like that, memories. So we can think about that or this scenario as a distributed system. So just a group of connected components, right? We can call them nodes from the idea of graph, or the same idea actually. Now, if you want to create minimum spanning tree from that, I think this is also very possible. I'll explain that. But first, this is the idea of distributed system. Think like Google. When you search something, definitely there are many website and there are many databases. There, the server as well. So and it's search from all of it, right? So that's basically the idea of searching in distributed system. Let's go to the method, the distributed system, and how we can implement Kruskal on that. So this is the steps. I'm going to tell you like it's very simple. So each component has its own tree. So basically, they have their own tree, and they just have to do minimum spanning tree, and separately, and finally just combine them. That's the idea actually. So each node communicates and merge components using this smallest edge. So this is basically the idea. The idea we have talked about, the Kruskal thing, the Kruskal algorithm actually. So the same idea you have to apply it here, but this is one thing which is different here. The nodes and the trees are in different location. Finally, you have to merge them. Let's go to um, the follow-up, question, which is real world ML scenario. How would you implement that? That is very simple in machine learning. That also, if you talk about the data connectivity thing, it can be used in that point of view as well. For example, sensor network feature selection. For example, you have many sensors, implemented and in different location. So they're all connecting data, right? And now finally, you have to find out that that MST really helps you that connects sensor efficiently. So you know that there could be redundant device, the loops. I'm talking about the loops. So you have to get rid of that. So it helps actually to find the most useful links, and which is the basically the purpose of ML. So that's what we do here, right? We efficiently do stuff, right? Let's go to the question 4. For a tree or graph-based feature index in a memory-constrained environment, compare slab allocation versus garbage collection as a memory management strategies. And they're like follow-up question: which option better support predictable latency for online serving ML system? So, I mean, the question is more like related to operating system. So I think we all know the basic concept of operating systems. We all have processes, right? This is the basic idea of operating system. So this picture actually describes it very well, that we have processes. When you have processor, it needs a memory, right? We have to assign memory in it. So that's why there are two categories actually. We can assign like contiguous memory. We can use that contiguous memory location. So what it does is basically it doesn't really separates those processes. Like the memory location is fixed, it sits in the fixed memory locations without really messing up with it. It just sits here. It's very easy to understand. For example, if you talk about the static array, you cannot change them later, right? But you can change dynamic array later. So this is non-contiguous memory location, because you can see this is the gaps, right? So basically it separates them, right? This is a different two um like processes, and there's two different memory location. It sits in two different locations, and that's how it works. But if you think about that, I think linked list can be a very good example. Linked list, does the same thing. You have information of the next node. It doesn't matter, right, whether next node is adjacent to that, so it can be anywhere. So we can actually do that using linked list, right? um, Also, graphs can be one of the example. Now let's talk about one of the important part of this question, which is slab allocation. What is that? It is one of the core concept in Linux system as well. So when you think about slabs, basically think about a drawer. Each drawer holds one size of the item, and it helps us, with the storing, and retrieving as well. So this is more like this picture, I think, can make you understand the concept, basic concept of slabs. So it is like object of the same type and size, such as tree, node, or graph, that sits together. So this is the concept of slabs, actually. If you look at the picture, you can see there is no fragmentation. Why is that? Because object fit exactly into fixed slot. If there is a fragmentation, that it would not have never happened, right? So this is the reason. Now let's talk about the garbage collection. It is a very interesting topic. If you think about, there's a robot. Let's say there's a robot, but it sometimes stops. Like it stops somewhere to collect something, right? Like to pick up unused item. For example, there's an item, it stops there. Hey, I have to pick up that, then I'll continue my work. There's a latency, right? So garbage collector is the same concept. So it is actually a memory management method where the system automatically finds and frees unused memory. Right. So when there's an unused memory, it finds that certain memory, culture, it detects no longer reference. For example, you don't have any hook in it, so it can be freed. So this is the concept of garbage collection. Now, if you understand these two things, then to answer the follow-up question is very easy. Which is better? Well, definitely, if you talk about the better thing, definitely we need something which has very low latency. Definitely, sub-allocation can be that, because we have specific drawers, right? We can easily find out the data from that. So that's the thing. We'll use slab collection, I think, because there's obviously flaws in garbage collection method. So that's all about it. That's all about the thing. I have also the documentation which clearly explains all the steps in it.